I want to talk about design in astronomy. And, we really have two explanations of how we and the world around us came to be. One possibility is that it just all happened. And I would define that to be evolution. And I would define evolution to be a purely natural, purely physical process or explanation of how we and the world came to be. Now, if there were an evolutionary biologist here, they would say, wait a minute. It's not that. It's variation in gene pool frequency, or some other such statement. I first heard that definition probably 35 years ago, and I scratched my head at the time. What in the world? I think it was an attempt to obscure, and I only have a little better understanding today. But let's back up a second. You see, evolution is not just about biology. There's also an elaborate theory of geological evolution as well. And there is a very elaborate theory or theories of cosmic evolution. It deals with the origin of the universe, the Big Bang, the formation of stars, the formation of the solar system, and so forth. So you got, at least in the natural world, if you will, you've got cosmic, geological, and biological evolution. But it's even more than that. There are theories of societal evolution, where government came from, where laws came from, where marriage came from, all of these things. And that sort of thinking has permeated all areas of human endeavor today. Almost everything you can think about, there's an evolutionary theory of how that works out there. Now, contrary to that is creation. And creation is the reverse of this. You're not relying upon a purely physical, purely natural process. Instead, you're appealing to a supernatural process. In other words, there is a designer behind all of this, a creator behind all of this. And so it's a supernatural process. Now, I've tried to define both of these possibilities as broadly as possible. Again, for the first one, to cover all aspects of evolution, not just biological evolution. But I want to be very specific about what I mean here. A person hearing just this much and no more could walk out thinking that I'm talking about Allah, the God of Islam, or I'm talking about some sort of pantheistic belief or a polytheistic belief. Make no mistake about it, I'm talking about Yahweh, the God of the Bible, Abraham, Isaac, and Jacob, incarnate in Jesus Christ, who came to this world to die for our sins and rose on the third day. That's who I'm talking about here. John speaks of Jesus being the creator, and that speaks well of the Trinity and upon the deity of Jesus Christ. So those are the two possibilities. Sometimes people ask, well, does it really matter what you believe about all of this? I mean, after all, if we all have Jesus in our hearts, we love Jesus, what difference does it make? And I would submit to you it makes a world of difference. If you believe that evolution is true, you're going to look at the world very differently than somebody who believes that creation is true. You're going to look at these institutions I talked about, such as marriage. There's a theory of evolution for marriage and a theory of creation for marriage. If you believe that marriage has evolved, then we should evolve marriage to the next step, which is? This was not a rhetorical question. Homosexual marriage. A few people said it, all right. But if you believe in creation, you believe that it's ordained by God, then we trifle with that institution at our peril. So, that's the big, great bridge on this one. And there's so many other aspects of life, not just societal, but also dealing with astronomy, with geology and biology, where you have two very different worldviews. And again, you're going to look at the world very differently. I read once about two men who were climbing a mountain, and they got up there, and it was quite a vista. And one man looked out and said, wow, he looked over these mountains nearby, and he said, "What? Look at that view." And the other man looked out and said, "Yeah, never before have I seen the backside of a buzzard in flight." They were both looking at the same thing, but seeing something very different, because their worldviews were very different. Let me try to illustrate this with a couple things, but see, the creationist sees design and purpose, design in the world around us, design in the creatures, design in ourselves, but also design in the cosmos, and purpose in all of these things. But on the other hand, an evolutionist tends to see chance and struggle. There's no design, there's no order, there's simply the chance and struggle that's to come together to produce what we see in the world. And that's because we begin with two very different assumptions. One assumption is theism, of God. And again, I want to be very specific which God I'm talking about here. And then the assumption of atheism. Turns out, if you truly understand evolution being a purely natural, purely physical process, there's absolutely no place for a creator. A creator is absolutely unnecessary. If you really understand creation, you understand that evolution isn't necessary either. Some people want to merge the two. They want to take basically the evolutionary ideas and then kind of put a God sticker on this, smiley face of God. He somehow did it. But we do have some specifics coming from Scripture about how he did it and when he did it. I have here, I want to illustrate by a few photographs. I have here a photograph of, anybody know? The Horsehead Nebula. Okay, it's distinctive because of that horse head sort of shape you see right there in the middle. And on the top half of the figure, you see a big red glow. And as an astronomer, I understand some of the processes going on here. When you see a red glow in a color photograph in astronomy, it's coming from emission of light from gas, predominantly hydrogen gas. It's the most common element in the universe by far, and so clouds of gas typically have lots of hydrogen. And there are some bright blue stars in the vicinity of this big cloud of hydrogen. And the ultraviolet radiation from those hot blue stars ionize the hydrogen atoms. They strip off the electron, and then very quickly the electrons find another proton and they recombine. As they recombine, the electron comes cascading down to progressively lower levels in the atom, and particularly when the electron drops from the third to the second orbit, it gives off a distinctive photon of light with that red color. It's over about 6,500 or so angstroms wavelength. A very pretty color, and that's what that big red glow is. And again, in a photograph such as this in astronomy, you're going to see a lot of red. When you see that, you're looking at emission from hydrogen gas. Now, on the lower half of the photograph, it's dark, and you'll notice generally the density of stars down the lower half of the diagram is less than the upper half of the diagram. What's going on down there is there's a big bank of dust particles. Now, when I say dust particles, I'm not talking about household dust, okay? We're talking about solid particles. These solid particles are very small, about the size of the particles in cigarette smoke. That's how small the particles are. And they're pretty thin in space, but when you pile them up over many light years, they start to add up. And as you try to pass starlight through those gas clouds, the dust clouds, the dust particles interfere with that light. We say it scatters it. It causes it to be kind of bent off in different directions. And if you're trying to look at stars through the dust, it gets obscured to the point that the stars are dimmed, and also they sometimes just black out completely. There are little knots in the sky, look like there's a hole in the sky almost because there's so much dust blocking there. And so it obscures our view. The stars you're seeing here in the lower half of the photograph are actually stars this side of that big bank of clouds. Down to the lower left, you'll see a big bluish glow there. That bluish glow has a star just this side of the dust cloud, maybe a little inside of the dust cloud, but not very far into it. And the light coming off that star is scattered off the dust particles. You can sort of say it reflects off of them. And it tends to do that more with the shorter wavelength light, which is blue. And so you get this blue glow here. When you see a blue glow amorphous like this in a photograph in astronomy, that's typically a reflection off of dust particles. And so we call that a reflection nebula. Now, this big dust bank on the lower half of the photograph is blocking out the light of more distant stars. So the stars you see here probably are this side of the dust cloud. It may be blocking some of that red glow behind it. But what's interesting, there's a little appendage that sticks up out of it. That's what that horse head is. It's a little appendage sticking up out of that big dust cloud there. We don't know what shape it has in 3 dimensions, but in 2 dimensions, projected as it is here, it's got that little hook, making it look like a horse head, like a knight on a chessboard or something. And that's what gives it that distinctive sort of shape. Okay, what is this a photograph of? Anybody know? Comet. Anybody want to guess which comet it is? Hail Bop. I always do that. I have to salute, Hail Bop when I say that. That was back in 1997. How many of you saw Hail Bop? That was a stupendous comet. People in New York City saw the thing. I didn't think that was possible anymore, but it was a very bright comet. It was on the other side of the sun. When it's at brightest, it's like 130 million miles away from us, so it was really far away. If we would have been real close to it, on the same side of the sun, I can only imagine how bright it might have been. Well, a comet consists of an icy nucleus a few miles across. In the case of Hail Bop, we estimate its nucleus is about 25 miles across, about the size of a good-sized county in some states. Not very big physically. It's down inside the head of the comet here. You're not going to see it because it's overexposed, the coma around it. The nucleus consists of ice, various types of ices, frozen water, but also frozen carbon dioxide, that's AKA dry ice. These are not rhetorical questions, okay? Dry ice, frozen methane, ammonia, all sorts of frozen things. Normally they're gaseous or liquid, but they're so cold because comets spend so much time away from the sun where it's very chilly that they're frozen in. And then interspersed with all that ice are little particles of dust once again. Very tiny. A few of them might be a little bigger visible to the eye maybe, but they're going to be very small. And comets have these very long orbits, very long elliptical orbits. If the sun's like this, a comet comes around like this once each orbit, comes close to the sun and goes out very far again. The planets would be down here, so it can go very far away from the sun. And out here it moves very slowly, and here it moves very quickly. Near the sun it does. And it's very cold out here, but very warm there. So when a comet comes close to the sun, the radiation of the sun heats the surface. It begins to evaporate some of those gases, and those gases then, ices, turn into gas. And when they hit space with zero pressure, they just spread out very quickly. And it goes out to tens of thousands of miles sometimes to form this large cloud of gas. And then the sun's radiation ionizes that gas once again, and you get electrons recombining. It starts to glow. It fluoresces. Sort of like how fluorescent light works, except it's electrical energy that's doing the ionizing. In the case of this, it's ultraviolet light from the sun. And it starts to glow. And then the sun's radiation and the solar wind begin to push the gas back away from the sun and the dust particles away from the sun as well, giving the beautiful tails coming off of the comet. And lastly, anybody know what this is? It's called the Ring Nebula. I picked some easy ones, didn't I? All right, this is an example of a class of objects we call planetary nebulae. When they first started discovering these more than 2 centuries ago, through a good-sized telescope, they look like a little disk. In fact, if you look at the Ring Nebula through a telescope, it looks like a little tiny disk. And that's what planets look like. So they had a superficial resemblance to the appearance of planets, and so they called them planetary nebulae. An unfortunate name, by the way. And for a long time, we thought that this ring was more like a bubble. It was a sphere. If you'll notice at the center of this sphere, there's a fairly hot star right there. The temperature is like 100,000 Kelvin, which would be like 180,000 degrees Fahrenheit in real temperature. And it's a very hot star. And we think in the past, a few thousand years ago, the outer layers of the star were blown off. When you hear that, you're thinking, some sort of nova eruption or something. No, it's not a nova at all. It turns out a lot of stars are very windy. We call them winds. It's just gas that's flying off of the stars. We're not entirely certain what starts the process sometimes. The sun is blowing off gas, but it's doing it at a very slow rate. Certain types of stars called red giants are doing it at a fantastic rate. Some of those can throw off almost at a rate of almost like 1,000th of a solar mass per year. I mean, that's a lot of gas being thrown off. And we think what's happened is this gas has gone out, kind of collected, and it's still expanding outward. It's like a big shell. And then the ultraviolet radiation from this very hot star ionizes the gas and gives you that very bright color there, bright light. By the way, these things can't last very long because as they expand, they get farther away from the light source, they get less dense, and also the star cools, and so they only last for thousands of years, and then they dissipate entirely and just disappear. We have now learned in the last few decades that the shape probably is not a sphere. It's probably an hourglass sort of shape, And we see some planetary nebulae do have, a dumbbell nebula as an example, has an hourglass shape because we're looking at it from the side. But if you look at it down the end of the hourglass, it's going to look round, won't it? So at one time we thought this thing was spherical, but in the last 30 years we've changed our mind. It's more of an hourglass sort of shape. All right. I showed you 3 pictures. Well, what did you see? Well, hopefully you saw beautiful photographs. I mean, that's what's the cool thing about astronomy. That's what got me going. I looked at Saturn. I was really hooked at that point. I always loved astronomy, but that really, really hooked me in. But I'm always amazed by the beautiful wonder. I like to look at the pictures. I love to look at things through the telescope. Through the telescope, it can be disappointing. You see these bright, colorful nebulae, and you think you can see that with your eye looking through the telescope. Well, many times those pictures were taken with a large telescope, and it's a 2-hour exposure, and your eye is only collecting light for about a tenth of a second. So these things are not nearly as bright as it would appear. But still, I enjoy looking at them. It's really a gas to do that. Also, I've shared with you a little bit of some of the interesting physical processes. You know, if you're going to do astronomy today, you have to study a lot of physics, and you understand then some of the physical mechanisms going on, and it's really cool the things we've been able to figure out by looking at these things and the instruments we use to study them. And you know, I really feel sorry for many of my astronomy colleagues because so many of them, it stops here. They see the beauty and the wonder of the grandeur, and they see the physical processes, but it all stops there. But you know, as a believer, I want to go on because I see the Creator's handiwork here. All right? You know, to me, the universe is like a giant billboard. It's like a giant billboard. It's advertising something. You ever gone along and seen a billboard and you really get your attention, you know? And, well, I'll illustrate for you. I was down in Jacksonville, Florida a couple months ago, and I'm driving along on the loop around the town, and I saw this picture, showed a picture of a cat, mostly its head, and it had the statement, something to the effect that every morning my human shaves the fur off of his face for no apparent reason. And my wife and I, you know, laughed at that, and after we laughed about it, we were past the sign, and I said to my wife, I said, what were they advertising? I had no idea. I went by the next day and I figured it was animal rescue, animal shelter, you know, to adopt animals, you know. But I had no idea. It was a great ad. It got my attention, but I wasn't paying. Well, I was driving down the interstate, you know, like 60 miles, 70 miles an hour. I needed to pay more attention, but I didn't have time to. How often does that happen? You see an ad like that on TV all the time. I don't understand modern ads. I really don't. Billboards are bad enough. Most times I watch a TV ad and I haven't a clue. They get down and turn to my wife and say, what were they? I don't know. Neither one of us can figure it out. So you see this big advertisement. But I fear many, many people, many astronomers have missed the point of the ad. They've missed the message is there, but they've missed the point of the ad. And you know what? I often think it's not a head problem. It's a heart problem. That's what it is if you're open to it. All right, so Psalm 19:1, the heavens do declare the glory of God, and the sky shows his handiwork. That's a cool verse. I've always enjoyed that one because it kind of zeroes you in back to what's important. But you know, you need to be careful that you don't worship the creature rather than the Creator. Now, I'm talking about design here. That's the whole point of this conference. And I have a kind of a conflicted relationship with the design argument. I think in biological systems, it's pretty clear to see design, but there are many people who really don't accept the design argument there. And in astronomy, maybe it's even a little more difficult to see. What I've discovered over the years, and this is through interaction with students and with other people, to giving talks and long discussions, what I find happens in a design argument, people who are already convinced that there's a creator find validation, okay? They find it easy to believe. In fact, they find it very consistent with what they already know or what they already believe. Nothing wrong with that, by the way. When you start getting bombarded with things that don't quite gel with what you believe, then you're going to have to do some soul searching there. But it confirms what you already know. On the other hand, if a person is convinced that there is no design, if he's convinced there is no designer, if he's convinced that there is no creator, then no amount of evidence will convince him. Again, it's not a head problem. It's a heart problem. And I can relate a number of examples to you. I've talked to people and offer evidence for creation, offer arguments against evolutionary ideas. And I've had a number of people, engage me in this. And when all is said and done, they can't really refute much of what I said. They're impressed by some of the evidence I've given. But the response is, I'm going to choose to believe in evolution. They basically admitted that that's not an intellectually honest or good conclusion to reach. Again, it's not a head problem, it's a heart problem. I am thoroughly convinced. And I'll illustrate this towards the end of my comments here. Okay, this is a photograph of a total solar eclipse. Saturn's the coolest thing I've seen through a telescope, but the absolute blow-away moment in my whole life was a total solar eclipse. You don't need a telescope to see that, so see, a telescope doesn't count here. Back in 1979, my wife and I, we drove from South Carolina to a little place called Ardborg, Manitoba. Anybody heard of the place? All right, nobody, okay. You heard of Winnipeg? You know where Winnipeg is? We were 100 miles north of Winnipeg, or I call it Winterpeg. And Manitoba is north of North Dakota, if you can imagine such a thing. Eastern North Dakota, which is the coldest part of North Dakota. And we went up there in February. And we drove, I was in school and had to get back, so we drove 3,500 miles round trip in 5 days in February in a 22-year-old car. Still have the car. For 2 minutes and 46 seconds of totality. And it was the most amazing thing I had ever seen in my life. It was not just the beauty of what I was seeing, but the experience of looking around. I got so excited I forgot to clamp down the camera I was using, and the thing was flopping around, and I had to recenter, and it was a mess. It never occurred to me that, hey, just clamp it down. It takes about a half a turn, And I'm pretty outgoing and talkative. My wife is not so much, and we played a tape recorder during thing, and we played it back later. And during the eclipse, my wife is just chattering away, and I didn't say 2 words. It was just the most amazing thing. No picture will do it justice. I'll try, but it won't do justice. By the way, there is a total solar eclipse on August 21st, 2017 that slashes across the United States. First one hitting the U.S. since 1979. And okay, this is a total solar eclipse. You're seeing here what's called the corona. It's the outer layer of the atmosphere of the sun. It's this pearly white thing. You can't see it really any other time except during a total solar eclipse. And the cool thing is, when the moon blocks out the sun, you look right up at it, and you don't need filters. You don't need anything. You're just standing there looking at this thing with your eyes straight away. It's the only time you can look at the sun without that. And of course, some of the brighter stars come out. It's really, really kind of cool. And then around the edge, this is a little overdone, I think, but around the edge of the sun, you can see these loops going out from the edge of the sun. These are called prominences. People sometimes think they're flares. They're not. Flares are something very different. This is a prominence, and these things are blood red. And in addition to the corona, you see these blood red prominences all around the edge of the sun. I saw all over the sun when I was looking at it back in 79. I was taking pictures madly, and about halfway through, I said, this is silly. I'm taking pictures. I need to enjoy it. So I just simply stopped taking pictures and just knelt down, just sat down in the snow, and just looked around to drink it all in, to see what I could take in at this point. It was way too fast. It was gone before it even started, it seemed like. So prominences, corona, the whole thing. And then towards the end of eclipse, you're not supposed to look at this, so I was snapping pictures as fast as I could, praying the entire time to the Lord, let me catch this. This is called the diamond ring effect. And if you look carefully at it, you can see that there's a little bit of the photosphere of the sun. That's a spot, that's part of the sun you can't look at. It's too bright coming through. There's the diamond, and there is the ring. Do y'all see that? And these little kind of burned out pinkish thing, those are prominences. They're overexposed here, I believe. And the corona is not really showing up either. But it takes a couple seconds to get that. But that's the diamond ring effect. And I think that's one of the better photographs of the diamond ring effect I've ever seen, and not just because I took it, but there aren't a whole lot of great ones out there. So the Lord was good. He answered my prayer and gave me a pretty sort of photograph there. So lunar eclipses, solar eclipses, total solar eclipses, partials are not that big a deal, but total solar eclipses are incredibly beautiful. Well, let's talk about this. You know what happens when there's a total solar eclipse? The moon comes between the earth and the sun, and so the moon's shadow falls onto the earth. It turns out the sun is 400 times larger than the moon. So if we wanted to make a model of the earth, moon, and the sun, the moon we could maybe make it an inch across. The earth would be 4 inches across, and the sun would be 400 inches across. That's like 34 feet across. Could we fit that in here? I don't know if we could fit that in here, could we? It'd be pretty close. I don't know how high the ceiling is, but it's getting there, okay? So you would have a hard time getting it in this room. That's the big difference in scale. But interestingly enough, the sun is 400 times farther away. So if something is 400 times larger than something else, but it's 400 times farther away, those two factors exactly cancel, and consequently the sun and the moon subtend an angle of a half degree. And so when the moon passes in front of the sun, it covers the sun up, but just barely. Now, what would happen if the moon were a little smaller or a little farther away? It wouldn't cover the sun up, would it? We wouldn't have total solar eclipses, would we? What if the moon were a little bigger, a little closer? Well, it would do too good of a job. It would cover up the sun too much, and that would have two effects. Number one, it would mean that the solar eclipses we see would not be nearly as spectacular. So this nice coincidence between size and distance between the two means that the eclipses we see are very, very spectacular, unbelievably spectacular, but it also makes them extremely rare. I read once many years ago, and I have no reason to doubt this, that on average, any given location on the Earth, you see a total solar eclipse about once every 4 centuries. So the average person in their lifetime is not going to see a total solar eclipse unless A, you're very lucky, or B, you travel someplace like Manitoba in the middle of winter. All right? And usually what happens when you look up these eclipses, you know, it's going across Timbuktu, quite literally Timbuktu in Africa, or it's going across New Guinea, or the South Pacific, or the North Atlantic, or Siberia, all these. It doesn't come across the United States very often. The one in '79 just hit parts of Washington and Oregon before it took off up into Canada. And so this one's going to come from Portland all the way to South Carolina. At any rate, these things are very rare and very spectacular. You know, there are some astronomers who specialize in eclipses, and just every year and a half there's an eclipse someplace in the world, and they go. So that would be a cool job, wouldn't it? Just traveling around the world. And people have seen like 30 or 40 of these things. There are some amateur astronomers and jet setters who go around and see these things too. So there are a lot of people going out there for those things. You know what? There are 150 or more, maybe closer to 200 now, known satellites or moons of planets in the solar system. And if you run the numbers, you find out that the vast majority of them don't produce total solar eclipses. And the few that do are grossly over total. They're huge. They're really big. And so eclipses are common and not very spectacular on these different planets. The only planet where you have spectacular and rare total solar eclipses is on the only planet where it really matters to anybody, you know? And I view total solar eclipses as a gift from God. I really do. I've seen some really cool things in my life, but nothing compares to a total solar eclipse in my estimation. This is a photograph of you can say it with more confidence, the moon, yeah. I have to tell this, I used to give planetarium shows when I was in grad school, and we would give, usually with grade schoolers, we'd show them, start off with we'd do a program on the planets in the solar system. Now, by the way, I used to do my shows with the Spitz A3P. Some of you know what that is, right? What is a Spitz A3P? It's that relic planetarium projector out in the lobby on display. So what does that make me, right? So anyway, I'm giving these shows, and I would start off by showing a picture of the surface of Mercury, and it's got craters on it. I'd ask, well, what's this a photograph of? And I always say the moon. I'd explain to him, well, it's a good guess, but it isn't. Here's why. And then I show him a picture of Venus, and it's got this crescent sort of shape. And well, a few of them might guess the moon, but they're a little, especially the sixth graders are now a little cautious, and no, it's not the moon. And so by the time I got to the moon, the third picture, the sixth graders wouldn't say anything, and the fifth graders probably wouldn't either. But those, God bless those third graders. I'd show them a picture of Mercury. What's this? The moon, and then I'd say, what's this? The moon, no matter how many times I slammed them down and saying, that's not right, they'd come back, the moon. You couldn't knock those kids down. It was amazing. I could have probably shown them 10 pictures in a row, and something else other than the moon, and they would have still said the moon when they thought so. So when I ask people in a group like this, what's this a picture of? You're supposed to say, very good. There's a little third grader in you all, isn't it? That's great. I love it. Yeah, this is indeed the moon. And it turns out, I guess about 10 or 15 years ago, I began thinking about the moon, and there are some interesting things about it that kind of escaped me for the longest time that gives us some design. First of all, the moon is very large compared to the Earth. Now, I'm not talking about diameter-wise. I've already indicated that the Earth is 4 times bigger than the moon. So the moon is 1/4 the size of the Earth. I'm talking here about mass. If you compare the mass of the moon, that's how much matter it has, by the way, and compare it to the Earth has 81 times the mass of the moon. So it takes 81 moon masses to equal 1 Earth mass. And you might say, well, that's an awful lot, isn't it? Well, yeah, except when you go look at the other planets. When you look at Mars, it's got a couple of tiny moons, and their planet is probably 1,000,000 times more massive than the moons are. When you go to Jupiter, they have a couple of those that are larger than our own moon, but Jupiter's 318 times the mass of the Earth. So it turns out the mass of Jupiter is hundreds or thousands of times more massive, and that's throughout the entire solar system. The Earth's moon is closest in mass to its parent planet, and none of the others are even close to that ratio. Now, that in itself isn't terribly important. It is interesting, but it's not terribly important. It does give us tides on the Earth. You could talk about those sorts of things. But here's the really, really significant thing, and it took me a while to get my head wrapped around this. When I did, I thought, oh, the moon's orbit is unique. All right. Now, the Earth rotates on its axis, right? It gives us day and night, and all the other planets do too. And that defines the equatorial plane. Suppose you have a planet. The planet here is its rotation axis. It's rotating around this axis, so the planet's going like this. If you have the axis going up vertically, then the equatorial plane is like this, all right? Most of the larger satellites in the solar system orbit their parent planets in the equatorial plane, right above the equator, all right? Now, the Earth is tilted by 23.5 degrees, so the rotation axis is not like this, it's tilted like this, and so as the Earth goes around the sun, it goes around the sun something like this every year, okay, right? What does that cause? It causes the year, but if with the tilt, what does it help cause? The seasons. Okay, very good. You paid attention in 4th grade or 3rd grade, whatever it was, right? So you got this tilt going like this. Now notice as I walked around on the platform here, that defined a plane like this, didn't it? We call that the ecliptic plane. That's the plane of our orbit around the sun. Now the Earth's equatorial plane, since the rotation axis is tilted 23.5 degrees, the equatorial plane is tilted like this, isn't it? All right? Everybody got that? You've got the ecliptic plane and the equatorial plane. Well, Saturn's orbit is tilted 30 degrees, more than ours. And its big satellites, most of its satellites, go on the equatorial plane. Ditto for Jupiter's satellites. There are a few rogue ones that go, small ones, far out that have odd orbits. There's one largish satellite, one of the outer planets. It's got a really whacked out orbit. But all the other larger satellites, go in the equatorial plane. Except for the moon. The moon doesn't orbit above the Earth's equator like this. It orbits in the plane of the Earth's orbit around the sun, the ecliptic plane. No satellite in the solar system does that. Yeah, a couple of you going, wow, or huh, yeah, that was the moment I had about 10 or 15 years ago. Yeah. Ooh, that's cool, that's interesting. Number one, that tells me that the origin of the moon is probably unique. I remember back in the late 70s, we were sending this neat space probe called the Voyager to the outer planets. How many people remember the Voyager? Those are one of the most fantastic ones ever done. And one of the justifications given for going to the outer planets was to study the satellites of the outer planets so we could figure out where the Earth's moon came from. In retrospect, that was kind of, well, just wrong. Okay, just wrong, because if you look at the orbits of those the outer planets, or satellites of the outer planets, they have a very different orbit than the Earth's orbit. Well, I believe the moon does have a unique origin because I think God specially made it, and he specially made it for his own reasons. I'm going to share at least a couple of them with you here this evening. But it's a very different orbit. So the origin's different. But here's something else. You all know, we talk about the tilt of the Earth. And the tilt of the Earth doesn't stay fixed. It does short term, but over longer term, it starts to move around a little bit. Why? Because other objects in the solar system, their gravity grabs hold of that, or the bulge of the Earth that's around the equator, and it tends to kind of nudge it. And over time, the tilt of the Earth would go up to 0 and down to 90 and back up again like that. That would really be weird. Here in Kentucky, we're about right now 39 degrees latitude. At some points, if this were going on, we would be in the Arctic and in the tropics at the same time. Think about that. In the Arctic and in the tropics at the same time. What would that mean? Well, it means at least one day a year the sun would be directly overhead at noon. It would be very hot, just like it is in the tropics now. And for at least one 24-hour period, if not more, there would be no sun at all, which would make it very cold. Would living organisms be able to adjust to that? I don't think so. I mean, you can't grow tropical plants into those kind of conditions, and Arctic plants can't grow in those kind of conditions either. So we've got segregation of different types of plants and animals, but we'd have a real problem here. Except for one thing. Remember the moon's unique mass compared to the Earth and its unique orbit? Those two factors combine so that the moon stabilizes the Earth's rotation axis. And it can waffle around by about 2 degrees max, and that's it. By the way, having a large satellite is necessary but not sufficient. Having the kind of orbit that it has is necessary but not sufficient. You need both of those characteristics to make this work. Fail at either one of those, and this stabilization doesn't happen. And again, this is the only planet where it really matters. It doesn't matter on any other planet because nothing is living there. So I think that's interesting. So it stabilizes the Earth's tilt over time. It also made physics possible. Well, stick with me here a second. Who literally wrote the book on physics? Well, okay, I'm talking about physics as we understand it. I'll put it that way. Sir Isaac Newton. Okay, y'all heard of that fellow, right? Okay, he had this great insight. For thousands of years, people had known that the moon went around the Earth every month, and they hadn't a clue why it did that. And he was thinking about this issue. There's a big debate, why it could happen. People were trying to figure this out. And he had a great insight. He hypothesized that the same force that compelled the fig to fall off the tree and hit him on the head was the same. It was a fig, not an apple. You've been misinformed. All right. And so it was the same force that caused the moon to go around the Earth each month. Now, he wrote this book called the Principia. That's the shortened Latin title for it. The exact title translated into English is Principles of Mathematics and Natural Philosophy. Natural philosophy is what we call science today. Until about less than 200 years ago, we called science natural philosophy. And in this, he laid out calculus. He invented calculus, his 3 laws of motion, his law of gravity and worked out the details of this thing beautifully. In fact, when I used to teach physics at the university, we would do almost nothing but Newtonian physics for the first semester of the course. Still works very well. He did all of this work by the time he was 22 years old. How many of you are at least 22 years of age? What have you done lately? I've never ceased to be amazed with the brilliance of Newton. But, the big problem he was dealing with was what causes the moon to go around the earth. And so we have here an image of the moon and the earth together, and the sizes are right. And I need to tell you here that the earth is very bright and the moon is very dark. You look at a full moon, you think, the moon is bright. No, actually, the moon is very dark. It only reflects about 5 or 6% of the light that falls on it. It's almost as dark as coal. Believe it or not. The thing is, the background sky doesn't reflect any. It's 0%. So that 5 or 6% compared to 0% is awful bright when it's in full sunlight. So the moon isn't nearly as bright as you think. So what they had to do here, they had to play a game with this. They had to decrease the Earth's brightness and or increase the moon's brightness. Otherwise, you wouldn't even see the moon. Other than that, this is a good photograph. All right, here's what Newton knew. He knew that the moon was 60 times farther away from the center of the earth than we were. Okay, when doing gravity, you have to take the center-to-center distance. We have to take my center of mass, which is about right here, and do the distance to the center of the earth, which is, let's see, my height above the floor and my height to my navel, plus 4,000 miles. My height above the floor and my height to my navel added to 4,000 miles is, to a very good approximation, equal to 4,000 miles. Very good. Okay, you understand limiting behavior very nicely, don't you? Okay, it turns out the moon is about 240,000 miles away. If you take 240,000 miles and divide it by 4,000 miles, you get 60. All right? So when you're considering your force of gravity, you're 60 times closer to the center of the earth when you're on the earth than when the moon is. Okay? Now, a few decades before, Galileo and people like him had measured the acceleration of gravity. How fast things are, it's 32 feet per second squared or 9.8 meters per second squared. Using his newly invented laws of motion and his calculus, he was able to figure out from the size of the moon's orbit, that was known, by the way, at the time of Newton, and the orbital period, which had been known for thousands of years, he was able to then compute the acceleration required to keep the moon going around the sun every month. And when he did that, he discovered that things on the surface of the earth were attracted 3,600 times more than the moon was. What's the relationship between 60 and 3,600? It's squared, isn't it? And this, if you're familiar with Newton's law of gravity, it goes as the what? Inverse square of the distance. Newton's law says every object in the universe attracts every other object with a force directly proportional to the masses and inversely proportional to the square of the distances between them. I've never memorized that. I just picture the equation in my mind and just read off the terms as I go through, okay? That's what I do. So what he did is he realized that the inverse square law gave him 60 squared is equal to 3,600. And if I lived to be 300, I would have never thought of that. But once someone like Newton points it out, it's obvious. Every time I taught this at the university in my physics classes, I just thought that was brilliant. I just felt like we're not worthy, because Newton was a brilliant man. And he knew it, by the way. So it was an interesting man, a very interesting man. I love Newton. He was incredible all the way around. So the inverse square law gave you the law of gravity, which tied it all together. And from that, you start putting things together pretty quickly, and physics takes off, and from that comes engineering, and from engineering comes things like electricity and air conditioning and planes and spacecraft and all that kind of stuff. That's the reason why technology started taking off 300 years ago, because we finally had a framework of science that worked very well. By the way, I don't agree with some of Newton's theology, but he was a devout man, and he was a student of Scripture, and he believed in God very strongly. Some references toward the end of his book, The Principia, where he makes it very clear that there's a creator, and even more importantly, that the study of the creator is a legitimate part of science. That's amazing, isn't it? Most scientists today aren't even aware of that because they want to make God unwelcome in science. This is a photograph of the Earth. Okay, the Earth has some interesting design features to it. I'm going to go quickly through this because quite literally books have been written on this subject, okay? Many of you may have seen some DVDs dealing with this. The Earth has a proper distance from the sun. If you get too close, it's too hot. Too far away, it's too cold. People have defined what we call the habitable zone around the sun and other stars where planets can be that can possibly support life. But it can't be just the proper distance. It has to be the proper size and composition because the moon is the proper distance from the sun, but it's dead as a doornail. It doesn't have the proper size and composition. Did y'all hear about the first restaurant on the moon, by the way? The food's out of this world, but there's no atmosphere. All right, so you need the right kind of atmosphere, not just an atmosphere, but you need the right kind of atmosphere. And the Earth's atmosphere is a nitrogen-based one. It's diatomic, which means you have two atoms that form a molecule of nitrogen. Ditto for the oxygen that we breathe. And it's superb. As it turns out, you don't want polyatomics, things like CO2, very much of it at least, because those are greenhouse gases and they hold in heat. I've heard about global warming and stuff. By the way, is global warming a good thing or a bad thing? Yes. Who said yes? It's the right answer. That's what I'm looking for. A little bit of global warming is a good thing, actually. Greenhouse effect's a good thing. You can't have too much of a good thing, but that's another issue. Liquid water. Liquid water, that's amazing. By the way, water, I think, is probably the most common molecule in the universe. It's absolutely essential for life. But as far as we know, this is the only place in the universe where liquid water exists. It always exists in the vapor or solid. There are some hints that there might be liquid water subsurface on some bodies out there, but those are hints. There's no definitive evidence of that. Comparing atmospheres, very quickly, I got the Earth and Venus there in the middle. You've got Mars to the right. The moon up above. I think that's Europa on the far left. That's one of the satellites of Jupiter they suggest might have a big ocean of water deep down under the ice on the surface. But again, that's conjecture at this point. I say water everywhere, but not enough to drop the drink, like from the rhyme of the ancient mariner. You look at the Earth there and the moon and Venus and Mars. And Europa, again, as I pointed out, lots of water throughout the universe, but precious little liquid water. The only place we know it exists for sure is on the Earth, and it's in abundance here. We see water in the interstellar medium. We see it in comets. We see it in asteroids. We see it in planets. We see it in the atmospheres of cool stars. It's all over the place. But again, the vapor is solid everywhere we look. So Venus is too hot. Mars is too cold. The Earth is just right. The moon is not. Sounds like Goldilocks, doesn't it? And the three planets or something here going on. And I want to close with talking about newly discovered extrasolar planets. Y'all heard about these things? Extrasolar planets, these are planets orbiting other stars. It's amazing. This discovery of this began about 2 decades ago. There are different techniques that are used to find these things. In most cases, we can't image these things, but we can detect them. Indirect, but that indirect measurements are often done in science. And so we have several methods. One of these is pioneered or actually carried out tremendously by what's called the Kepler mission. That's an image there or an artist's conception of the Kepler space probe. It had these cameras on a big wide field telescope, and it was monitoring for about 3 years, monitoring continuously about 150,000 stars. Every 20 or minutes, 22, 25 minutes, it was measuring those 150,000 stars to accuracy of almost 1 part in a million. That's pretty good. I measure star brightnesses, and I'm doing good to do 1 part in 100. So I'm envious of this kind of work. And they were looking for transits of planets around other stars. Well, what is a transit? Well, suppose you've got a star sitting here. It's that big yellow ball there, and you've got a little planet there, a little red ball, and it's going around the star. And you'll notice on the first position on the left here, it's distinct from the star, but then it passes in front of the star, and as it passes in front of the star here, it dims It's going to block out some of the area of the star there, and you'll see that down here's a light curve. The light of the star is constant, and then it drops, and then it recovers. Now, you need to be looking at this orbit edge on. If you've got a planet orbiting a star like this, you're not going to see anything, are you? But if it's orbiting like this, you can. So you got to have good orientation to see it. If we were looking at the sun from another star and watch the Earth pass in front, we'd have to be in the plane of the Earth's orbit, which is not a real wide range of possibility there. But if you look at 150,000 stars, you're going to find a few, you would think. And when you do that, you'd find that every year, every 365 days, the sun would dim by about 1 part in 10,000, certainly reachable by Kepler, and it would dim for about 13 and a half hours. If you're measuring every 20, 30 minutes, you're going to pick that up, aren't you? So a solar-type, Earth-type planet would be detectable by this methodology. And here's an actual light curve. I think this is Kepler 13b, I'm not sure, 30, I forget the name, but it's one of the Kepler stars. And you'll notice there, as you come across, the light dims and recovers like this. And by the way, I studied professionally eclipsing binary stars. We do a similar thing with eclipses of stars like this. So it's the same sort of science. It's just different kinds of objects. One's a star and one's a planet instead of being two stars, in the case of what I look at. And the result is we've found now over 1,000 probably orbiting planets of other stars. In fact, suspected probably 3,000 or 4,000. So we're finding scads and scads and scads of stars. Well, why look for extrasolar planets? Well, first of all, to prove that planets are common around other stars, and then maybe prove that solar systems, that is, systems of more than one planet orbiting around stars is pretty common, and then prove that Earth-like planets are common, and then prove that life is common. You surprised by this? This is driven by evolution, isn't it? Okay. And I found over the years some creationists are kind of nervous about this because they're saying, well, we're looking for planets. We can't have planets. That's why. I think some people are afraid that maybe they'll find some Earth-like planets or places where life might exist or something like that. Well, what have they found? Well, they found that planets are indeed common. You got over 1,000 known planets and such selection effects that you only find them if you're edge on. Those are pretty good statistics getting in there. And we're finding out we probably have 3 or 4 other planets that will be confirmed in the next few years. We're finding solar systems are common because now we've got like multiple systems, like 170 multiple systems now. Many of those have like 4 or 5 planets around some of those stars. But Earth-like planets are not common. You could say in the solar system with 8 planets, one of them being like the Earth because it is the Earth, that's a small sample size, isn't it? But when you have over 1,000 planets, that's a large sample size now, isn't it? And of the 1,000+ planets we know about, how many Earth-like planets are there? 1. The Earth, you got to count the Earth. Okay, don't forget the Earth. Somebody back there is going 0. No, you got 1, all right? That's a good sample size. And see, my expectation as a creationist is that we're not going to find any Earth-like planets. We're not going to find life elsewhere. And so has the science borne out what I predict? Yeah. Yeah, so don't be afraid of this. The science is actually on our side. I'm amazed at how many times we slam the doors shut on Mars being an abode of life, and yet they keep hoping that somehow there will find life on Mars. They're doing the same thing with all these. There have been several planets trotted forth as being possibly habitable, and one of the first one they had, it took me 5 minutes on the internet to find out that was impossible because of the problems with that star, for instance. It was orbiting. And it's amazing how they don't tell you the bad side of these things. Very optimistic on these things. They're leaning on it tremendously. So there have been no habitable planets yet. I'm very safe in that statement. No habitable planets yet. Before you can have life, you have to have a habitable planet. But even if you have a habitable planet, it doesn't mean there's life there, does it? But we haven't found a habitable planet yet. So the science is very good on this. And so I think the design inference is very strong that livable planets are exceedingly rare and at this point, I would say unique within the large sample size we have. And I would expect as our sample size increases, that's my expectation, my prediction, is that will hold up. And it's held up so far very well, I think. So I think the solar system is unusual to the point of being unique, hosting a planet that can harbor life, and some other things about the solar system that help that out. And last, I'll close with this, what we call the anthropic principle. This was a term coined 1972 by Brandon Carter. It was a statement that there are certain characteristics of the universe that make the universe suitable for living things like us to exist. So there are a number of characteristics, if you will, or coincidences, if you want, what do you want to call it, that seem to make the universe suited for humanity's existence. It's not just the earth, but characteristics of the universe itself, physical constants, physical laws, all sorts of things. Back probably over 30 years ago, there were two astronomers named Barrow and Tipler who wrote an exhaustive book on this subject. It was called The Anthropic Principle, and they gave the history of the anthropic principle and all sorts of other cool things. And they went on over 1,000 pages, giving different forms of the anthropic principle, the history of it, discussing it in complete detail. And you know what their conclusion was? Barrow and Tipler said that the universe only appears that way. They basically admitted that there are design features in the universe, but rather than concluding that the universe was designed, they concluded that the universe appears to be designed. That's getting back to head and heart, isn't it, again? You know, I found that people who are true seekers are open to this message, and I'm very compassionate, and I want to engage these people. But I found a lot of people who have closed minds about this, and I won't spend a lot of time with people like that because my time's too valuable for that. It's very blunt about that, but there are many, many people out there who want to argue, but they don't want to approach it with an open mind. You have to have at least the possibility of being convinced, and I think it's very sad when people cannot be convinced of this. But there are true seekers, and those are the people I like to talk to.